Oh, it's already recording. Okay, good. Okay, so welcome back to Organic Chemistry 2341, our 253 section at 8 a.m. on Thursday morning. So what we're going to do is we're going to do a really fast version of module 6.2. And for those of you who didn't watch the video that's on YouTube, go ahead and watch that YouTube video for the more detailed course. I'm just going to draw your attentions to a few things, and then we're going to continue on with section 6.3 today. Okay, so 6.2. The key here is that we're learning about the mechanism associated with a substitution reaction. Now, we're learning about these substitution reactions where we're using nucleophiles, which are going to be Lewis bases, and we're going to see how the mechanism progresses by the fact that both molecules have to be in the transition at the same time. Okay, S for substitution, N for nucleophilic, 2 for the fact that it's bimolecular. Both of the reactants have to be there at the exact same time. So that's what this means, and we're going to go ahead and talk a little bit more about that. So the general idea here is that you're going to have something that's a nucleophile. Okay, your nucleophile is going to have a negative charge, or it's going to have a lone pair. Okay, that negative charge, and that negative charge is usually on a lone pair, or a lone pair is going to make a new sigma bond on some other center, preferably something like a carbon. In this case, we're calling our carbon center our electrophile. As it's starting to form this new sigma bond, the bond on the carbon with some other electronegative atom, in this case, we're looking at bromine, is going to take its 2 electrons away from its bond and create a charged species that leaves. Okay, so we have some words to think about here. Go ahead. Question?
Are you sharing a screen for us to see, or?
Apparently not.
Oh, okay.
Thank you. All right. There, you should see a screen now. Okay. All right. Let me go ahead and mute my watch. Okay. Can we see the screen now? Yeah. Okay. Sorry about that. Okay. So the few things we need to look at here is in our reaction, we have to substitute one group, usually on a carbon center, with something else. Okay. So we can think of this as a Lewis acid base reaction. Okay. And in this case, the nucleophile is going to be our Lewis base. A Lewis base is something, of course, with either lone pair or a negative charge. Okay, it has electrons willing to share to make a new sigma bond. Okay, so whenever you think Lewis base, think nucleophile. Whenever you think nucleophile, think Lewis base. Nucleophile should always have that charge or a lone pair. Okay, now the part that leaves is what we call the leaving group. Okay, and the other part of our Lewis acid base pair is our Lewis acid, right? So our Lewis acid is the electrophile. And you're going, well, how is carbon electrophile? It doesn't have a positive charge on it. This is where bond polarity comes in. Whenever you look at a carbon compound, you want to look for the polar bonds, okay? The polar bonds tell you what kind of partial charge is going to be on that carbon. If we, in this case here, we have a bromine here. Bromine is more electronegative than the methyl group, and therefore it's pulling electron density here, giving us our partially positive charge on carbon. That makes our carbon the target of the nucleophile, and it makes our carbon the electrophile, or our Lewis acid. Okay, so it's willing to accept electrons to form a new sigma bond. Okay, so nucleophile is a Lewis base, electrophile is a Lewis acid. You can use those interchangeably. Okay, so now, what happens when you break that carbon bond with that bromine bond? That bromine becomes our leaving group, and because it's leaving with its electrons here, we end up with a negative charge. Okay, so this is what we call a nucleophilic substitution reaction. Okay, so let's talk about some details. Okay, the first thing we have to do is name everything. So the thing coming in with a negative charge or lone pair is always our nucleophile. Okay, the carbon on our substrate, or the thing we're reacting with, should have a halogen on it. In this case, we're using halogens as leaving groups. We'll discuss other leaving groups as we go. Okay, but we're going to have some polar bond between carbon and some other electronegative atom. And then we're going to use the electrons from the nucleophile to make a new sigma bond. We're going to take the old sigma bond and form a negative charge. Now, but Professor Irvin, there's something wrong. You had a negative charge on one side of the reaction and a negative charge on the other side of the reaction. What keeps it from going back and forth? Well, if this is also a good nucleophile, it can be reversible. But I can teach you how to know which way the equilibrium is going to lie. Okay, so the first thing we have is our nucleophile. Think negative charge, think lone pairs, think Lewis base. Okay, the next thing we have is our electrophile. Think a carbon with a polar bond, preferably with a more electronegative atom, a halogen, an oxygen, a nitrogen. Those are the kinds of things that are going to have a polar bond. That's going to give you a partial positive charge on carbon, and it's going to be the target of your nucleophile. Okay. The next thing we have to do is about leaving group. The leaving group is the bond that's breaking. Okay. So the bond that's breaking, to help the reaction progress, you want to make sure your leaving group is a stable, weakly basic molecule or ion. Okay, so it can leave, like water can leave on some cases, and I'll show you how that happens, or you can leave with like a halogen. Okay, now I say weakly basic molecule or ion. Okay, so we're going to have to remember our acid base stuff about our conjugate acids and our conjugate bases, and we're going to get into that in a minute. Okay, so these reactions are S for substitution, N for nucleophilic, 2 for bimolecular, meaning both species have to be in that position at the same time. And these are in the wrong order. Okay, so, sorry, I want to use this energy diagram. There we go. Okay, so start of the reaction, we have our nucleophile. Which is the nucleophile? The one with the negative charge. All right, and we have our electrophile. What's that? A carbon with a polar bond, okay, which makes that our electrophile. So that's where the reaction is going to happen. The electrons from the nucleophile are going to make a new bond with the electrophile, okay? But instead of breaking a bond and making a bond, we're going to go through a transition state where we're making one bond and breaking one bond at the exact same time, okay? When we do this, this is our transition state, okay? This is a high energy state. There's technically 10 electrons around that carbon, and therefore it's not going to last very long, 10 to the negative 12 seconds kind of thing. And as soon as we start breaking this bond, we cascade down into products. And now we have substituted our bromine for our nucleophile. Okay, so this is what happens. And in our reaction coordinate diagram here, notice our SN2 reactions always have one hump. We have one transition state. We have the nucleophile come in, form that transition state, and then substitute the leaving group and have our products. Okay, so if bromine is a really good nucleophile, we can actually probably go back up here and have our equilibrium. Okay, but in this case, I'll show you why bromine is not strong enough to make this a highly reversible reaction. Okay, so that being said, you have to have both molecules there at the exact same time, okay? Which means that the concentration affects the rate, okay? So if you have one equivalent of, in this case, methyl chloride and one equivalent of your hydroxide, both concentrations are important, so that sets your rate. Now, if you double one of these and keep one of them the same, it will double the rate because you have twice as many of these molecules that can be hit by these molecules, okay? Now, if you double both of them, now twice as many of these can be hit by twice as many of these, the rate quadruples, okay? So both concentrations of the substrate, usually the carbon compound with a leaving group, and the nucleophile are important in this. And because of that, we have, this is to the power of 1, this is to the power of 1, we add those together, and that's why we get an overall second order reaction. Okay, So what does this mean? That means our rate of reaction is dependent on concentration. And we're going to talk about that in a little bit too. Okay. So questions about that, the making that transition state and why the concentration is important for these reactions. All right. So that being said, this kind of reaction where it happens all at once has a special name, okay? It's called a concerted reaction, and it's a concerted reaction because you're making and breaking a bond at the exact same time, okay? So, but one of the cool things about this is because you're making a bond and breaking a bond at the same time, you must make the bond 180 degrees from the bond you're breaking. They can't be occupying the same space at the same time. So when we do that, we end up with what we call inversion of the carbon center. This is only important, well, no, this is important because when you have chiral compounds, you will be inverting the chirality of your carbon center. Okay. So in this case here, what we want to think about here is that, let's say we have our carbon compound here and our leaving group is over here, okay? And because this is our leaving group, this is the bond that's breaking, we have to have our nucleophile come in from this direction here. And it has to come in 180 degrees from here and to start forming that new bond, okay? And then this bond will break, but then because the new bond is forming on this side, the actual thing flips backwards like flipping an umbrella inside out, okay? Think of it as you're forming that, it's gonna flip like an umbrella inside out, and that's gonna change that position in space of those three other compounds. In this case, we don't have to worry about chirality because they're all the same group, but this always happens in an SN2 reaction. So if you have a chiral carbon, pay attention. Okay. So we have several factors that affect the rate of the concerted reaction, and this explains why the concentration of both things are important, okay? So they are, the first thing is the idea that we have to have enough energy for the nucleophile to go past the electron clouds of those groups to start forming that new bond, okay? So think about it, all of the other groups have electrons on the outer shell, this has electrons on the outer shell. We have to have enough energy to overcome that electron-electron repulsion to start forming our new bond, okay? To form that transition state. Once we get to that transition state, it's actually very easy to break that bond and cascade down into products. So the first thing we have to do is have energy. And in this case, it's kinetic energy. So we have kinetic energy that allows it to overcome the sterics and collide, starting to form that new bond. Okay. So how do we get kinetic energy? Well, we get kinetic energy by raising the temperature. We need to have more molecules that have enough of the activation energy or the kinetic energy to go. And we've already looked at this in the last section here, but I wanted to reframe that because concentration is also a factor here too. By raising the temperature and raising the concentration, we will have more molecules that have enough energy that when they start to collide, they can form that transition state. If you can form that transition state, you can go to products. If you don't have enough energy to overcome the sterics, your reaction will not go. Okay. All right. So, and there's some math associated with that. The important thing here is that you have an effect with concentration, which is, no, you have an effect of temperature and activation energy. So at 0 degrees C, we only have 7 collisions per 10 trillion molecules. Just raising that 10 degrees and going to 10 degrees Kelvin, we've actually increased that to 200. So it's a factor of 3. And so therefore it goes 3 times faster just by raising that. 3 times more collisions, sorry, 3 times more collisions, and the net rate is actually double that. Okay, so because we have more collisions at higher temperatures, we have more products being formed at each collision, and therefore we have a faster reaction. Okay, so the next thing that happens, remember, we're overcoming steric hindrance. I'm sorry, we're overcoming electron-electron repulsion. Okay, so not only do we have to have enough energy to do that, we have to have enough space to be able to start forming that too. And if our groups get too big here, then we're looking at something where we can have enough energy, but we don't have enough space. And that's called the steric factor. Okay. So as the groups that are attached to the carbon you're trying to attack get bigger and bigger and bigger, you can't overcome that. And therefore, the rate will go down. Okay. So there's an equation for that, and you can go look at my explanation for that. But I like the visual here. Okay. So the idea here is that if we have a good nucleophile here, a nucleophile, it has enough energy, but it comes in at the wrong angle, it's not coming in at 180 degrees, no reaction. So that's a high energy state, we get no reaction. Okay. Let's say you're almost in the right place and you have a large group, and so you get repelled by the large group. Okay. So that's also a high energy state, and you don't form the product. Okay. But let's say you have a nucleophile with enough energy and in the correct orientation, and it's in this small window of opportunity where the sterics allow it to come in, overcome that electron-electron repulsion, and let it start forming that new bond. Once it starts forming that new bond, the other bond will break and you go to products. And so we're taking the lowest energy path. It's like taking the path between two mountains in there. You don't want to climb this peak and then this peak to get to the next side. You want to find the lowest part right here. And when you find that lowest part, that's the most likely pathway. And that most likely pathway is going to be the fastest path. Okay. So, question on that? So overall, what we have is a negative charge, a lone pair, is going to come in and start to form a new sigma bond. Okay. We're going to have the lone pair from the current sigma, we're going to have the two electrons from the current sigma bond start to leave and go and be on that group that's going to leave. And therefore, we form a new sigma bond with our nucleophile. We form a new species that has that lone pair from the sigma bond on the leaving group, and we have inversion of the carbon center. Okay, so
Dr. Irvine, I have a question.
yes.
So are these exogenic or endogenic reactions?
Most of them are exergenic or exothermic, yes. So, and the reason we do that is when we talk about bond energy, we're going to see that we're actually going to be giving off free energy because the bond we're forming is going to be stronger than the bond we're breaking. And that's another reason
Thank you.
a good leaving group is a good leaving group, because it's going to be fairly stable as the anion or molecule that leaves. It's going to be, maybe not as stable as with when it had the sigma bond, but it's going to be not a really big energy barrier for that molecule to leave, and therefore it is going to be exergenic. Okay, so like I said in the diagram before, we're going to make that transition state. We have to have enough of the kinetic energy to overcome the sterics. We have to have electrons ready to do the bonding. And then once we get to that transition state, it decays rapidly into our products. Okay, so key thing about stereocenters is you always get this inversion, okay? You have to get inversion because the bond you're making has to be 180 degrees from the bond you're breaking. Therefore, the groups that are on here are going to do that flip like inverting an umbrella. Okay, so this is particularly important when you have your chiral compounds. So if you had an R2-bromooctane and you substituted that with a sulfur compound here, you're going to go through that inversion during the transition state, and your product is going to be the S compound. And if it was 100% SN2 reaction, meaning you didn't go through any other mechanism, you should have 100% optically pure compound. Okay, so This also happens on rings, even though rings are kind of are trouble to get in your head. You can see it very easily in rings because if you start with a compound that is cis, where both of the substituents are on the same side of the molecule, because we have to come in and attack 180 degrees from the leaving group, we're going to end up with a compound that's going to end up being trans. Remember, cis is where we have both the groups substitutions on the same side of the ring, and trans is when we have them on opposite sides of the ring. Okay. So it happens in rings as well as in our chiral compounds. These are also chiral, however. So, but we get to see this in the ring as well. Okay, now one of the cool things about Fisher projections is it's really easy to figure out how to draw them because when you have these substitution reactions, if your leaving group is on one side of the Fisher projection, your reactant is going to end up on the opposite side. Okay, so that's our substitution. We're not creating a mirror plane here. We're creating an actual inversion of that stereocenter, so it looks like we're creating a mirror plane. And in this case, we actually made something with an internal plane of symmetry, making it a meso compound. However, if we had just one substitution here, we're still going to invert the center, but we're going to end up with a specific stereoisomer. Okay, so that is how our SN2 reactions invert that carbon center each time. And in the case of rings and or chiral compounds, how you look for that inversion of center. Okay, so when we write SN2 reactions, we always think about nucleophile. And when we think about nucleophile, we think about a lone pair. Doesn't have to be a charge, it just has to be 2 electrons willing to give up to make a new sigma bond. We're going to have some carbon center, and then we're going to have some leaving group here. Okay, and we'll talk about the nature of the leaving group here. And so what's going to happen is our electrons are going to come in here to make our new sigma bond. Our electrons are going to stay with our leaving group to give us our nucleophile with a sigma bond to our carbon, our inverted center, plus our leaving group with our lone pair. And again, our nucleophile can be, if our nucleophile is negatively charged, our leaving group is going to be negatively charged. Okay, if our nucleophile is neutral, it depends on the nature of the leaving group. Okay, so there's several things that affect the rate of these reactions. Okay, just like before we were talking about, sterics and energetics and stuff like that. The nature of the leaving group is very important in here. That's why we started with alkyl halides. Alkyl halides are really good leaving groups, have really good leaving groups because typically chlorine, bromine, and iodine are some of our best leaving groups because they form stable ions. Okay, so because our leaving group gains the electrons from that sigma bond, it usually leaves as a negatively charged species, and therefore, if the more stable that negative charge is, the better a leaving group it's going to be. Okay. The next thing that's important is the reactivity of the nucleophile. If the nucleophile is very nucleophilic, in fact, wants to share its electrons really, really strongly, it's going to react faster than one that might be a neutral compound. It'll say, I can share my electrons, but I don't have to. So that's going to make it a slower one, but it still can react as a nucleophile. Okay. So another thing that affects it is solvent. Okay, we're going to talk about solvent, and typically we want a polar solvent in this because we're supporting a negative charge as our nucleophile, and typically, and a negative charge as our leaving group. So we want something that is polar. Okay, we're going to talk about 2 different types of solvents: a polar protic solvent, which is one that can hydrogen bond, and a polar aprotic solvent, which is one that can't hydrogen bond. The next thing we look at is the structure of the nucleophile. Okay, is the nucleophile really big or really small? Is the negative charge centered on a single atom or on multiple atoms? is the nucleophile just a lone pair, or is it truly charged? Okay, so if a nucleophile gets too big and bulky, it's hard to fit into that little teeny space between the groups that are on that carbon center. So if you have a big nucleophile, it's going to react very slowly, sometimes not at all. Okay. Okay, so let's talk about the leaving group. The best leaving groups are those that make stable ions or neutral molecules. Okay, stable ions or neutral molecules. And the way to think about this is that, okay, what makes a stable ion? Okay, a stable ion is going to be something that is a really weak base. Okay, so, but how do we know that it's a weak base? Okay, well, let's look at how strong it was as an acid and look at its conjugate base. So in the case of HCl, HCl has a pKa below 0, which means the chloride ion is a very weak base. It was a very strong acid when it was protonated, but now that it's deprotonated, it has that ion, it's a very weak base. Okay, when you have something that's a very weak base, it's a very good leaving group. Okay, so when we think of that, we want to think of anything with a very low pKa is a good leaving group. Anything with a very high pKa of the conjugate acid is a very poor leaving group. So let's look at that in the function of, can you use that to see if the reaction is progressing or not? Okay, well, yes, we can. So what we're going to do is we're going to look at this reaction here with this, where is it? There it is. This group, right, this sulfur attacking group, it's our nucleophile because it has a negative charge on it. And our leaving group right here is going to be OH because it was breaking this bond here. Okay, so we can't tell directly from the negative charges. So let's look at their conjugate acids. So if we added a proton to this group here, it would become H2S or hydrogen sulfide, and it has a pKa of around 7. Okay, so that's the pKa of the conjugate acid. But we need to know how basic this thing is, right? So we need to look for the pKb. So luckily, pKb is always 14 minus the pKa. Okay, so in this case here, we're going to be 14 minus the pKa, and that turns it into 7. You can remember from Gen Chem that pH went from 0 to 14. So 14 is the highest differential you can have. Therefore, in our case, you take the 14, subtract the pKa, and you can see how strong a base it is. Okay, so that gives it our pKa of 7. So it's a okay base. It's not a really strong base. Strong bases would be those with negative numbers. Anything above positive, they start to get weaker. Okay, so let's look at the leaving group here. If we protonate that to make it an acid, its pKa is 15.7. Okay, if we take 14 minus 15.7, we get negative 1.7. Okay, which means this is the stronger base. Okay, all right. The leaving group can never be the stronger base. You always want to go to the weaker base to make this reaction drive. So by looking at the conjugate acid strength and calculating the pKa of the leaving, pKb of the leaving group, you can see if the reaction is going to go or not. In this case, we have a lower number, meaning the reaction mechanism is going to lie in the direction of that higher number, which means the reaction will not go. So we can use the conjugate acid base theory to tell us whether or not our reaction will progress. Okay, questions on that? Okay, so then that means that if we were to put a table together with leaving groups, we could probably just see what the pKa of their conjugate acids are and see if they're a good leaving group or poor leaving group. So in the case here, we're going to look at the good leaving groups. Notice all the good leaving groups, all of the conjugate acids are negative. Okay, OH as a leaving group is bad, but look, water as a leaving group is good because it leaves as a neutral molecule. But its conjugate acid is the hydronium ion, and it has a pKa of this 0.7. So if your conjugate acid here is negative, less than 0, you have a good leaving group. Okay, so let's look at some other things that might be leaving groups, like the other halogen, fluorine, right here. So there we go. If we look at this, we have fluorine, its conjugate acid has a pKa above 0. Hydrogen sulfide has a pKa above 0. Hydrogen cyanide is above 0. Hydroxide is above 0. So that makes all of these bad leaving groups because these are all above. Okay, so, well, you know, we have a lot of things with alcohols on them. We probably want to use that as a leaving group, but it won't leave by itself because it's too strong a base. Okay, its conjugate acid is too weak. Okay, how can we get around that? We can trick it. Okay, notice over here we have sulfonate right here. So sulfonates are kind of like organic versions of sulfuric acid. They have some carbon sulfur bond to them. Okay, so we can trick alcohols, and we're going to talk about this in chapter 11, to be good leaving groups by converting them to sulfonates. Okay, so we react our alcohol with something, and when we do that, we can do that with either a structure like this, where we have a toluene sulfonic acid, a methyl sulfonic acid, or a trifluoromethyl sulfonic acid. And because all of these have a pKa below 0, they're all very good leaving groups. Okay. Hard to hear. Let's see. My mic's all the way up. Okay. Yeah, my mic's all the way up, but I will try to speak clear. Okay. So in this case here, we can trick our OH into being a leaving group right here by converting it to one of these sulfonic acid derivatives, and that turns it into a much better leaving group right here. So we'll talk again more about that in chapter 10. All right. So we have some current trends in nucleophilicity. One is charge. Second is basicity. So we have to think about our acid-base, polarizability, solvent, and the effect of substituents, or sterics. Okay, if the substituents get too big, the nucleophile can't work. So I'm going to go on these kind of briefly. Okay, the negatively charged nucleophile is always stronger than its conjugate acid. Okay, so for example, the stronger the conjugate, the weaker the conjugate acid is, the neutral component, the better a nucleophile it's going to be. So notice that the charged species with a negative charge is always going to be stronger than the neutral species. Even though this does act like a nucleophile because of the lone pair, it already has a negative charge on it. It's more reactive than the neutral species. Okay. So that's the first thing to think about. So when you're looking at good nucleophiles, look for the charged species first, and then there will be some uncharged species that still act as nucleophiles. The next thing we want to look at is basicity. The stronger the base, the more nucleophilic it's going to be. Okay, so in the case of the oxygen series here, alcohol has a pKa of about 16, 17. Hydroxide, if we look at the water, it has a pKa of 15. This has a pKa of 4.7. This has a pKa, if it was protonated, around minus something, and then this is minus 1.4. So this is going to be our strongest base because it was the weakest acid, and therefore it's going to be more reactive of our system. Notice this is all with the same atom. We're all comparing oxygen to oxygen. Okay. So the next thing we want to look at is electronegativity. The more electronegative the atom is, the less likely it is to share. Okay, so in the trend of down a single row here, we're going to see that electronegativity directly correlates to nucleophilicity. The lower the electronegativity, the more nucleophilic. So in this case here, our carbon has, is around a 2. Our fluorine is around a 4. and oxygen and nitrogen in the middle, and it trends exactly with nucleophilicity. The weaker the electronegativity, the stronger the nucleophilicity. So the other thing that affects it is charge, okay? So if you already have a negative charge on an atom, it's going to be a much better nucleophile than if it was a neutral species. And one of the reasons for that is that in the case of this, we have a negative charge on this side of the reaction, and we have a negative charge on that side of the reaction. So we're going from a single charge to a single charge, okay? That is going to be our fastest substitution reaction possible. However, the lone pair on our neutral species can still act as a nucleophile. But when it does, we're going to end up with this oxonium cation. We're going to have, this is protonated. Now we can lose this proton in the next step, but we still made a charged species. When we made that charged species, it is going to be slower than if we made a neutral species, and therefore the reaction, the charge on the atom is going to make it a better nucleophile. Okay. The last thing I want to talk, well, the next thing is sterics, okay? If you get too big a bulky group right here, remember you have to repel the electrons from the other atoms as it comes in to make our new sigma bond, okay? If you have a whole bunch more surface area to repel on your nucleophile, then it's going to be harder for it to react. In fact, in the case of this one right here, this is the classical T-butyl anion here. It is so bulky, it never acts as a nucleophile, okay? So, but when you have smaller substituents on here, they become better nucleophiles, which means that the methoxide here is going to be a stronger nucleophile than the isopropyl counterpart, and this is almost non-nucleophilic at all. It just sits there and acts like a base. Okay. So the trends in nucleophilicity go with, you know, those different things there. And we also have, the next thing is polarizability. Okay. So within a group of materials, we saw that nucleophilicity was a key here. And the electronegativity was a key here. I'm sorry, electronegativity was a key. But polarizability is a key because let's say you have your charge and it's spread out further away from your center, okay? And so that they can be tugged on by fields or charges nearby more than if you had a very small atom that had a very tight around the core. It's very hard to pull on those electrons. So when you have larger atoms that have these big groups of electrons, big fluffy atoms, they are more polarizable. And more polarizable is more reactive because it can start to pull and form our new sigma bond early on, because they can be pulled very far away from the center of the atom, as opposed to a very tightly bound electrons where you can't pull them very far, meaning that you can start forming this bond at a much greater distance. And if you're starting to form the bond at a much greater distance, it is more reactive. Okay, so we can take those general trends and turn them into a table of good nucleophiles and bad nucleophiles. Okay, so I'm gonna pull this up right here. So notice it's not just pKa here, okay? We have a combination of different things, okay? So we have on these, we have a negative charge right here. And in the case of these three right here, they are very polarizable. We have a sulfur, which is a big atom. We have an iodine, which is a big fluffy atom. And we have azide. And azide is actually has a negative charge, but it's conjugated, so the negative charge goes back and forth. So the negative charge is spread out over that, so it is also very polarizable. These are what we call our excellent nucleophiles. They have charge and they have polarizability, okay? The next group we have is what we call good nucleophiles. And these have charge, right here. And these are not necessarily as polarizable. This does have a little bit of polarizability, and this does too. But notice we now have a neutral species in here. Okay, ammonia, the nitrogen on ammonia can act as a good nucleophile, even though it's not charged. Okay. Then we have our fair nucleophiles. Notice that chloride and fluoride are in this group here. Chloride and fluoride are in this group because of their lack of polarizability. And acetate and neutral oxygens are in this group as well. The acetate is because it actually has only half a charge over here. This is a full, this is polarizable because if it comes in from this direction here, it can pull it in that direction or that direction. But it's still a very good nucleophile because it's a negatively charged nitrogen. This one right here has a resonance structure. It has the charge on the two carbons, but it's also a weaker acid. So think about the chloride and fluoride here being weak because of their polarizability, the neutral species because they're neutral, and the acetate because it's has multiple resonance structures. Okay, so if you don't think you can figure that out on an exam, go ahead and memorize this of excellent, fair, and good nucleophiles. Okay, the next thing I want to talk about is solvent effects. Okay, and in solvent effects, we have to have a polar solid, so it's got to be polar. Okay, if we have nonpolar solvents, we can't support the nucleophile or its charge, and therefore the reaction can't progress. But we have two kinds of solvents. We have a solvent that can hydrogen bond, and we have a solvent that can't hydrogen bond by itself. Things can hydrogen bond to it, but it can't bind. So think of our polar solvents, our polar protic solvents, as hydrogen bonding, and our polar aprotic solvents as dipole-dipole. Okay, so that's their major interaction here. So we also have, we can have hydrogen bonding to ion, ion hydrogen bonding, and dipole ion right here. Okay, of those, which is stronger? The hydrogen ion bond is stronger and therefore can support our nucleophile. Our dipole ion is still a pretty good bond, and that way it can support our nucleophile. Okay, so some of the ones we have for polar are water, alcohols, and carboxylic acids and amines if they have hydrogens on them. Okay, some of the polar aprotics are things like, this is called DMF or dimethylformamide. We have a nice carbonyl here to give us a dipole. This is called dimethyl sulfoxide, and we have a nice S double bond O. So whenever you think carbonyl, you're going to think one of those atoms is going to have a partially positive charge, one of those is going to have a partially negative charge. There it has a permanent dipole. We have a more electronegative atom here, so we have a permanent dipole. Acetone, nice carbonyl. Now ether, yeah, it does have a permanent dipole because it has lone pairs. And these lone pairs give it a permanent dipole, which means this oxygen also has lone pairs, which gives it a permanent dipole. So when you think of polar aprotic solvents, no hydrogen that can hydrogen bond, but they're still going to have a permanent dipole. Of course, the protic solvents are going to have that charge, that hydrogen to hydrogen bond. So what does this do? Well, in the case of some species, you can use either because it can be supported by either system. However, you can have systems where the hydrogen bonding helps you or the hydrogen bonding hurts you. And this is specifically relevant in the case of our halogens, okay? In the case of our halogens, right here, when we have our halogen system and we use them in a polar protic solvent, okay, so water, methanol, etc., iodine is going to be more nucleophilic than fluorine, even though fluorine has a higher electronegativity. Why? Okay. Well, the reason for that is that if we looked at the way it bonds in our, where is, there you go. It bonds in our system here. it is protonated by the species by that hydrogen bonding, and therefore the iodine is a stronger acid in this if it was hydrogen bonded to. And therefore in polar protic solvents, things that can hydrogen bond, iodine is our better leaving group. Okay. Now, that's because we have hydrogen bonding to an ion. Okay. And it's creating a conjugate acid in the system, and iodine's the stronger acid. What if we don't have that? What if we just have that dipole ion interaction? If we only have that dipole ion interaction, we don't have that formation of that conjugate acid, and we have a weaker interaction with the system, making our nucleophile less solvated, having a less of a solvent shell around it, and therefore it changes the trend. Excuse me. In that case, the trend reverses. Okay. Most other ones, it just kind of controls the rate, but in the case of halogens, if you use a polar aprotic solvent like acetone or DMSO, it changes the nucleophilicity. Fluorine now becomes the more nucleophilic. That's the least basic of them, but it's more nucleophilic because of the reaction with the solvent. Okay. So that's very important, because when we start doing reactions like this, we're going to start seeing what solvent it's in. If the solvent is methanol or water, iodine's your strongest. If the solvent is acetone or THF or DMF, one of those solvents that we talked about there, it's going to be reversed. So you can actually intentionally remove an ion and replace it with a fluoride by using a non-protic solvent, a polar aprotic solvent. Or you can replace a fluoride with an iodine by using a polar protic solvent. So you can go back and forth between ions just by choosing your reagent and your solvent. Okay, so the net reaction is bimolecular reactions tend to be exothermic or exergonic. Okay, the transition state involves both molecules at the exact same time, making it a bimolecular reaction. Strong unhindered bases are good nucleophiles. That's taking into account our strength of our anion and our size of the substituent. Strong hindered bases are poor nucleophiles because they can't repel that electron-electron repulsion. They can't overcome the electron. Weakly polarized bases are good, weak polarizable bases. Remember, iodine and bromine were very strong acids as their protonated form, so they're weak bases. So they can be good nucleophiles if they're polarizable. But weak, less polarizable bases are poor nucleophiles. These are things that are neutral or things that have a smaller atom in them. Okay. Polar aprotic solvents will speed up the reaction because the nucleophile is not supporting that charge enough. It's a very bare charge and it will react. And you can go watch the other video to see that full explanation. Polar protic solvents can hydrogen bond, therefore can slow it down and invert the reactivity in the halogens. Okay. So, can you trick your reaction? And the answer is yes. You can trick the reaction because you can either make it a thermodynamic product or you can make it a kinetic product by changing your solvent or changing your reactant. Okay. So in the case of halogens, all of them are pretty good nucleophiles except for fluorine. I'm sorry, are good nucleophiles, but they're also good leaving groups except for fluorine. Okay. So that means that we can interconvert them, and we can interconvert them using an SN2 reaction. Okay. So in this case, we're actually exchanging an iodine with a chlorine by using acetone, a polar aprotic solvent, and it converts it to the lithium iodide, which is the thermodynamic product. We're making a stronger bond with the chloride because it's a shorter bond. Therefore, it's our thermodynamic product. But which is the stronger base? Okay, let's see. Iodine is HI as its conjugate acid. HI is a stronger acid. So that means it's going to be a weaker base. So we're driving it by that thermodynamic force. Okay. But can we switch it the other way? We can by changing our by changing the nature of our leaving species. Okay. In the case of this, we can actually convert our chlorine to the iodide. Okay. Remember, we just did the reverse reaction and we found it was thermodynamically favored to have the chlorine there. But we can convert our chlorine to the iodide, the kinetic product, because we can remove the chlorine as it's formed. Remember, I said SN2 reactions are typically reversible, although they'll lie on one side of the air based on which is the stronger base. So it'll always go to the weaker base, right? So in this case, we're actually going to the stronger base, the chloride ion right here, because it's the weaker acid, conjugate acid, but we're tricking it. We're making that precipitate out of solution. So even there's a small back reaction that allows the chlorine to act as a nucleophile. I mean, there's a small back reaction of the iodine not being as reactive as the chlorine. As soon as the chlorides form, it comes out of solution. So we can actually use solvent to help us get the kinetic product over the system instead of the thermodynamic product. Remember, we're talking about the nucleophiles and we're talking about the base strength of the leaving group. We want the weakest base whenever possible to give us our thermodynamic product. Okay, so what you're reacting with also has a strong thing to do it. So every reaction we're going to look at that has an electronic component, doesn't make a stronger bond, doesn't make a better linear, whatever, and it's going to have a steric component. So this is the steric component of the SN2. Now, like we can think about it, the less steric demand on our system, the faster it should be, because we have to have one group come in and one group leave at the exact same time. So Sterics plays a major role in our reaction rate. So if we just have a methyl group here, its relative reactivity rate is 145 times that of having the one with an ethyl group on it. Okay, so all we've added is this ethyl group. So we've replaced one hydrogen with a methyl group there, and the reaction decreases in reactivity. Okay, so let's add another methyl group. So let's go to a secondary carbon here. That's going to decrease it by a factor of almost 1,000. And then by the time we get to our tertiary right here, we almost have 0 SN2 reactions happening to it because we cannot get the formation, the starting of that formation of that new bond 180 degrees away from our leaving. So sterics plays a role. Methyls are always fastest. Primaries are pretty fast. Secondaries can be a little bit slower. Tertiaries never happen with an SN2 reaction. Okay. So, and again, that has everything to do with trying to get that electron or electron repulsion of there. So there also has an effect on the size of our nucleophile, right? Because if our nucleophile gets too big, even though we have one small group there, it can still inhibit the reaction. And we call that steric hindering. All right. So that tells us something about the nature of our steric at the exact center we're actually doing the reaction on, right? But what about sterics on the bulkiness of the group if you only have one group, okay? So let's talk about taking that primary alkyl halide and adding just one methyl group to it here. And we'll just have it a relative rate of 1. What if we added another methyl group to it? Right here. So, well, it's a straight line, right? No, remember these have free rotation and they're in the zigzag space here. Adding that one extra methyl group gives it that extra little bit of rotation. There's a little bit of swinging around there and it decreases the rate by about 20%, just having that one extra group there. If we instead of putting a methyl group on there, replacing this hydrogen with a methyl group, we replaced it with 2 methyl groups here. It actually goes down to 3% of that reactivity. Now we have both of those groups spinning like a propeller out there, and it's hindering that reaction from happening. Even though we still only have one carbon attached to it, this entire group has gotten really big, and it slows the reaction down. And on our last example here, even though it's still a primary carbon. We have this big, huge, bulky group out here, you know, like an umbrella, just blocking everything coming from that direction. And our rate goes very, very low, less than 0.003%. So questions on sterics. So there's a lot of things to look for: how strong the nucleophile is, how good the leaving group is, whether or not it's going to go based on the basicity of the leaving group, and now sterics. So now the last thing we want to talk about is the idea that we can have these substitutions at our that are adjacent to an sp2 hybridized carbon. Okay, and so when we have them adjacent to an sp2 carbon, they are, so we still have, it's an sp3 carbon with a halogen on it, or a leaving group on it, and we have it adjacent here with a sp2 hybridized carbon. They tend to be fairly reactive, okay, because the sp2 can lend a little bit of electron density or can help it go. But you cannot do an SN2 reaction on an sp2 hybridized carbon. You have to do a completely different reaction. They do not act as a display. So you can have you can have double bonds in your system, but you must have an sp3 hybridized carbon to react with. Okay. Now, part of the reason that works is that you can get this alignment of the double bond with the new incoming bond being formed. They'll align, and there's a little bit of hyperconjugation associated with that. And we can do a resonance effect and an inductive effect to make it go a little faster than an sp2 hybridized carbon wasn't there. That's why we have, if we look at just a methyl group and an allylic group, which is one of these, this double bond, this right here, will line up with that new forming bond here and help stabilize it, making it go faster. And when you have a benzene ring, you have a whole bunch of these to donate into the stabilization here. And so the benzylic goes faster. But again, this is on the sp3 hybridized carbon, not on the sp2 hybridized carbon. And we'll talk about more of that next year, or next semester, when we go into the benzylic and allylics, etc. Okay. All right. So the last thing I think I want to talk about here is the idea that, okay, when I talked about the SN2 reaction, I had the reactant coming in and having to form that transition state with the leaving group, and that reaction went at a specific rate. Let's call it relative rate of 1. Okay. What if you make your reactant group on the same molecule as the one with your leaving group? Okay. So if we do that, the reaction tends to be 5,000 times faster. This reaction right here is 5,000 times faster than this reaction, even though electronically, sterically, and everything is the same. Why? Okay. In the case of this SN2 reaction, we have to wait for this to have enough energy to diffuse for this substrate. It has to come in at the exact right angle. And then if it misses the collision, they diffuse away and they have to wait till they come back again. Okay. So in the case of the intramolecular one, they're bound together. So this is going to be trying to hit it many more times because it'll never diffuse away. It's just going to flop around, come back, come back, come back. So there are more collisions in an intramolecular reaction than in an intermolecular reaction. Therefore, intramolecular reactions to form rings are thousands of times faster than forming the analogous straight chain material. Okay, questions on that? Okay, so net thing is SN2 has a lot of factors, so we need to review those and kind of get it straight in our heads where they are. But that's not the only mechanism we have available to us. The other mechanism we have available to us is what we call an SN1 reaction. And so what's an SN1 reaction? Well, S was substitution, N was nucleophilic, 2 was bimolecular. So one must be monomolecular or unimolecular, okay? So if it's unimolecular, that means it depends only on one molecule to form something that is reactive, okay? Which means that it only matters is the concentration of the carbon material that you have your leading group on, okay? Because something has to happen to that to make it reactive. So we are thinking about it as what we call a first order reaction. It only depends on the concentration of the substrate. You can increase and decrease the nucleophile without affecting the rate much, but you must do the increase of the one with the leading group to make it go faster. Okay, so what does that look like? So that means we must be doing something different, right? So in the case of an SN1 reaction, we typically form a carbocation, okay? So we have a two-step reaction at least, and in this case, I'll show you a three-step reaction with a carbocation, okay? So what's the first thing that has to happen? Because we're not actually just making and breaking a bond at the same time, we have to break a bond first, okay? So in this case here, we're looking at a tertiary chloride here, okay? Why tertiary? Well, we're making a carbocation, and what we learned was that carbocations, the most stable carbocations are tertiary carbocations. So it'll be the easiest carbocation to form if we already have a tertiary species, okay? And we're gonna heat it up to give it enough energy to overcome that bond, and we're gonna break that bond first. And when we break that bond first, we have a formation of a carbocation. Notice that carbocation is a higher energy state than the neutral molecule, okay? Okay, so it is very reactive because it absorbed energy to get there. And so it has extra energy that it wants to give away. So it wants to react with something, okay? And in this case, it has to overcome the electron or electron repulsion energy barrier to react with something that has electrons it wants to form. In this case, we're going to use water. Neutral water is going to use one of its lone pairs to come in here and start to form a new bond. Once it does that, we end up getting to our intermediate here, okay? Another intermediate. Why is this another intermediate? Well, it's a charged species. It really wants to lose that proton to become a neutral species, okay? So we actually have to go through another transition right here where you have a base come in and start to pull off our proton, and then we end up at our final product here, which is much lower in energy than our starting material. And in this case, we formed an alcohol. So the key thing in an SN1 reaction is it's unimolecular. It must break a bond first to form a carbocation. That carbocation can then react with either a neutral species or a nucleophile, okay? If it reacts with a neutral species, we have to go through a secondary step where we remove that proton to get to our neutral product. If that was a charged species, it'll cascade to products and do that. Okay, so in this case, our general theme is always going to be, we have some polar bond, we have some leaving group. Some leaving group can support that negative charge. When it leaves, we change our hybridization. This is sp3 hybridized carbon right here. This is an sp2 hybridized carbon with an empty p orbital, okay? So that means that we can have the nucleophile come in from the top or the bottom and get a product. Once our electrons are from our nucleophile form that sigma bond, we end up with our product here. So in this case, we actually have a negatively charged nucleophile, so we don't have another transition state. We have our final product. Okay, questions on that? So it looks like we have two requirements for an SN2 reaction. It's got to be at least a secondary, but preferably a tertiary. If it was a secondary, it might rearrange. And we have to have a really good leaving group because it has to be a really low energy bond to be able to break. So start thinking whenever you see something with a good leaving group like bromine or iodine, and you have a tertiary carbon, start thinking, ooh, I'm going to form a carbocation, and that's going to change the way we look at it. Okay, so first thing that has to happen is we have to break a bond. So we have to add a lot of energy to the system to break that bond and create a high energy intermediate. Okay, our high energy intermediate has changed the hybridization of our carbon, and we're left with an MDP orbital. Now, because we have a charged species here, carbocations can react more readily with neutral species like water or alcohols than if they didn't have that positive charge, because those are weak nucleophiles. So we can actually put these groups on. We can use weak nucleophiles with our carbocations because our carbocation already has a high energy state. Okay. So after we have our formation of our carbocation, we can then have anything come, any Lewis base with a lone pair willing to share can come in and interact to form a new intermediate. In this case, it's a charged species. Then, of course, our last step is some other molecule of water is going to act as a Lewis base to deprotonate our intermediate to give us our final product here. Again, this deprotonation step is only required for our neutral Lewis base, our neutral nucleophiles. All right, so if in SN2 we always had inversion of stereocenter, what happens in an SN1 mechanism? Okay, so because we had a bond forming and breaking 180 degrees apart, we always had inversion of center, but we have a different structure here. We have a carbocation. Our carbocation is trigonal planar, and we have a lobe on the top and a lobe on the bottom. That gives rise to the idea that your product can be either attacked from the top, which would give one isomer, or the bottom and give the other stereoisomer. So SN1 reactions are always racemic, or a mixture of the R and the S. Okay. So that's very different from the SN2 reaction, where we always have inversion of stereocenter. And in SN1, we always have a mixture of stereocenters, 50-50, because there's no difference from the top of the molecule or the bottom of the molecule. Okay. Which means whenever we do a reaction on something that is optically active, in this case, we have the 2-bromo butane, and it was 100%, we purified it, we made sure it was exactly 100% optically active, and we just boiled it in water, and then it lost all optical activity. And it's like, oh no, I converted it to the alcohol, but half of it's R and half of it's S, therefore it's a mixture of R and S, and unless we separate them by some enzymatic method or some special method, they are going to be a mixture of isomers. Okay, so if solvent played a role in the formation of SN2, does solvent play a role in the SN1 reactions? And the answer is yes. We want it to be able to support that carbocation. So the other thing we have to do here is we can actually, instead of the reaction, the solvent being just a bystander, we can actually use it as the reactant. Okay. Now, in the case of something where you have a polar protic solvent, it will help support the carbocation as it goes, and then that solvent can act as a weak Lewis base and react with that carbocation. So in the case of using water with our system, just boiling water with our substrate here, our tertiary bromide here, it will create our tertiary alcohol. And this is called hydrolysis, because we're taking off that bromine and adding OH. We can do that with neutral alcohols too. We can just do it with ethanol or propanol, and that'll displace and give us our, in this case, an ether right here after we lose the hydrogen in that second intermediate. We can even use the acetic acid, or in this case, formic acid, to give us a formate ester here, and that's called acidolysis. Notice that on our previous table with SN2, these were all poor nucleophiles, okay? But because we're forming that reactive species, that carbocation, they can all react very readily to form our final products. Okay. So the key in our polar protic solvents here is it needs to, number one, start to hydrogen bond with our leaving group. Okay. So it's starting to hydrogen bond with our leaving group, helping to polarize the carbon halogen bond. Okay. That makes it easier for it to leave. Now, as we're starting to form our positive charge on carbon, the other side of our molecule, in this case, the oxygen, can start to stabilize that positive charge. So several water molecules, the oxygen side is going to help stabilize that positive charge above and below the plane, while the hydrogen bonding portion of our things help stabilize the ion going. Remember, our ion hydrogen bonding is one of our really strong bonds. That strong bond is helping the reaction go to form that intermediate. Okay. So how does polarity help? Well, in the case of this, if you can have a protic solvent helping, then it's going to help stabilize the charge being come off, and it's going to start hydrogen bonding with your leaving group before it ever even reaches that transition state. If you have a very polar solvent like water or methanol compared to a less polar one like isopropanol, because it's got more of the R groups on it, or T-butanol, those are less polar solvents, even though they have a proton. The more polar solvent is going to decrease the activation energy and let the reaction happen faster. Okay, because again, lower activation energy is a faster reaction. So if we compared the reactivity between isopropanol and methanol, because methanol is more polar, it's going to have a lower activation energy and it's going to have a faster reaction. Even though they're both going to stabilize the charge and they're both going to react as Lewis bases, that polarity does affect the reaction. Okay, and one more slide. Okay. So let's do this comparison. I'll do this one comparison. In the case of this, we're going to use the exact same reactant right here, and we're going to react it with water. Water is our nucleophile in both of these cases. Okay. In this case here, we are using 100% water. So that means 100% of the solvent can hydrogen bond with our bromine to help it remove the bromine to form the carbocation. Okay, in this one right here, we've taken 90% of the solvent and turned it into acetone. Still a polar solvent, but it's less polar than water. We still have to add water because that's our nucleophile right here. But by adding the acetone to it, we now have mostly dipole-dipole interactions, making it a less polar solvent, and the reactivity drops. Notice the relative reactivity with the acetone is 1. With water in there, it's 400,000 times faster. Okay, so the polarity of our solvent has a big impact on that activation energy to form our carbocation and that stabilization of our carbocation. And then we also have a lot more of the water around to act as a nucleophile. So we're doing it on two fronts. We're forming the carbocation faster, and we have more of our nucleophile around to react. Okay, okay. All right, I'm gonna stop there for today. We're right here at 9:20, 9:19. So what I will do here is I'll go ahead and stop recording. If you have questions, we're going to finish up the last 10 slides on, let's see, this is on Tuesday, and then we're going to start chapter 7, and we're going to learn about elimination reactions. So we'll have SN1, SN2, and then we're going to learn about E1 and E2 and how to compare and contrast all 4. So I'm going to go ahead and stop recording.